All right, so what I want to look at today are a couple of general properties of the logarithms, and then also examine the graph a little bit. Because if we understand the graph and the parent function here, then we can transform it however we want using the same transformations that we've been using, okay, for all of our other parent functions. So first of all, though, let's look at a couple of properties. And some of these you saw, hopefully, as you did your independent practice for today. So, for example, and I have the natural logs and then just a general logarithm side by side so you can see these work for both. The log base a of 1, or the natural log of 1, is always going to be 0. Okay? And that's because anything to the 0 power is 1. Now, notice what that's giving us. If this were an exponential function, the x-coordinate is what? If we're doing a logarithmic function, the x-coordinate would be 1, and the y-coordinate would be 0. Okay? So guys, our x-intercept for every logarithmic function, unless it's shifted or stretched horizontally or something, it's always going to hit that point 1, 0. Okay? So keep that in mind. That'll give you a nice frame of reference. And remember, that makes sense if you remember that this is the inverse of an exponential. And the y-intercept of the exponential is always 0, 1. Okay? Remember, inverses, we switch the x and y coordinates. So it's 1, 0 for our x-intercept. All right, so that's one property. Another thing is, if you're taking the log of the base, it's going to equal 1, because, of course, the base to the first power is the base. You had one like that on your practice. This third one here is just a restatement of the fact that these are inverses. So if you have what we looked at yesterday, you don't necessarily have to write this down again. But notice here, the log of the exponential, when they have the same base, gives us just the exponent. And here, if we have the exponential with a log in the exponent, we'll just have what was inside the log. They undo each other. And then lastly, this is what Callan was asking about earlier, and we were explaining here. If you have logs on both sides of the equation and the bases are the same, then what you're taking the logs of must be equal. Okay? Now, like we had said, you can't take the natural log of two different things and get two different results. Okay? Or I should say, you can't take logs and get the same results when you took logs of different things.
These are all the properties?
These are some of the properties of logarithms. We're going to learn some more rules for like working with logarithms here in the next few days, but these are some of the basic properties that we need to keep in mind. Okay. Now, these first two we're particularly going to use because notice they actually give us 2 points for every logarithmic function. Here, whatever the base is a, and when a is your x-coordinate, what's going to always be your y-coordinate? 1. Yes. 1. Alright? So right there, guys, you should be able to get 2 points on your graph really easily. Now we can get other points as well. Okay? So let's actually use that to graph the log of x. Okay? F of x is the log of x. I'm going to change the scale a little bit on my y-axis. I'll leave the x-axis the same. But what's 1 point on our function log of x? 1, 0. Okay? We know we're going to have the point 1, 0. Because every logarithm has the point 1, 0. What's a second point? 10, 1. Okay? The base here, remember, is 10. So we have the point 10, 1. Okay? Now, when you're coming up with points for these, you could think of these in their exponential form. If I were rewriting this as an exponential, I would have 10 to whatever the power f of x is, and that will equal my x coordinate. So in this case, I could just plug in different values for y. That'll give me my x coordinate. Alright? So if I plug in 0, I get 1. If I plug in 1, I get 10, like we already saw here. If I plug in 2, I'm at 100. Okay, so I'm way off the graph now. That's why I changed the scale on my y-axis. Now, in order to draw this accurately, we need to recognize a couple of other things here. We need to identify what the domain and the range are. Okay, what is the domain for the logarithm function?
X is greater than or equal to 1? Or is it all
What do you guys think about that? X is greater than or equal to 1.
To 0.
What?
Greater or equal than 0.
Greater than or equal to 0?
All
All real numbers? What do you guys think? We've got some options. What? We got another vote for greater than or equal to 1?
greater than or equal to 1.
Let's think about it in this form right here with the 10 to the f of x power equals x. If I'm raising 10 to a power, can I get 0? Is there something I could raise 10 to get 0? No. Is there something I could raise 10 to get, say, a fraction? So I'm going to the left of 1.
Mm-hmm.
Yeah, I could raise it to like the -2 power or something like that. So I know x can be to the left of that -1. Is there anything I could plug in for the exponent to get a negative value? No. Okay, I have a positive base. No matter what I plug in, I'm going to have a positive. So my domain should be just greater than 0. Okay, Santiago was the closest. We didn't want to equal to 0. It can't be equal to 0. But you're right. It would be x is greater than 0. Okay? And in this case, x equals 0 would be a what? It would be a vertical asymptote. Okay? Alright, that's an asymptote. So now, that's significant, guys, because now we can sketch this side of our graph, okay? We'll get the other side in a sec. But notice we're going to approach the x-axis but never cross it. Okay? Now we need to think about our range. And especially if you look at the exponential form of this, the range actually should be pretty easy to determine. What is my exponent allowed to be?
Any number.
Any real number, okay? And that's shown because this will go through this point 10, 1. It's going to continue to increase forever. Now it's increasing really, really slowly because we don't even get up to 2 until we're all the way over at 100. But it will continue to increase forever. So our domain is x is greater than 0. Our range is all real numbers. I'm going to draw that a little better here. Okay? Okay. So range, all real numbers. Any questions about that? Okay. Let's try another one. Let's say we have the log base 2 of x. Okay? The log base 2 of x. What would our domain here be? X is greater than 0. Alright? X is greater than 0. And what would the range be? All real numbers. Okay? Still the same. We still have a horizontal, or a vertical asymptote at x equals 0. Okay? Someone give me a point on the graph.
1, 0.
1, 0. Alright? 1, 0.
2, 1.
2.
And then good, 2, 1. We have the point where we have the base, and anytime the base is the x-coordinate, the y-coordinate is going to be 1. Okay, so here's 2, 1. Here's our point 1, 0. Okay? And then again, if you think of this in terms of its exponential form, it's really, really easy to find points. The exponential form here would be 2 to the g of x power equals x. Okay? So now if we plug in different values for y, we can find the value of x really easily. So if g of x is 2, it's x is 4. So here's the point 4, 2. Okay? If g of x is 3, then x had to have been 8. Alright, so you're the point 8, 3. And then let's keep going. What's our next point? 16, 4. Good. And then finally 32, 5. That's all that'll fit on our graph. Okay? So there we have our exponential, our logarithmic function, the log base 2 of x. And this needs to approach the y-axis. Okay. Okay. Does everyone understand how we got this graph? Alright. So what would we end up with if we did, let's say, h of x, and we said that that was 3 log of 2x? What's going to happen? Vertical stretch. Alright, so the point 1, 0 is going to stay on 1, 0, but instead of 2, 1, I'm going to be at 2, 3. And instead of 4, 2, I'm going to be at 4, 6. Yeah. Okay, and then here we're up at 9. There we go. Here we end up at 12. and instead of being at 5 at this point, we're going to be up at 15. So here you can see it's still going to approach the y-axis, but the whole thing, oh wait, I went to 20 instead of 15. There we are. Okay. There we go, it's just stretched. So you see here, we don't have to learn this whole new thing. We just use the same transformations that we did in the past. Okay? Let's do j of x. And let's say that this is 2 plus the log base 2 of x plus 3. What's going to happen to all the points on my original log base 2 of x function?
Up 2, left 3. Left 3.
Good. 2 up and 3 to the left. Very good. 2 up and 3 to the left. So again, I just take all these points. The point 1, 0 is going to go, let's see, 3 to the left and 2 up. So it's going to be right here. Instead of 2, 1, we go, again, up 2 and 1, 2, 3 to the left. Notice our asymptote is going to shift 3 to the left as well. So we should draw that. Okay? But all of these points are going to go up 2 and 3 to the left. Up 2, 3 to the left. Up 2, 3 to the left. And up 2, 3 to the left. So we have that, and notice it looks exactly the same as the original one. It's just moved because we just translated it. We didn't stretch it or shrink it at all. Okay? So now you have another parent function. You can add this to your sheet. Remember, we had the sheet with the absolute value, the cubic, the quadratic, the radical function, the reciprocal function. Now we have the exponential function and the logarithmic function. Okay? And what you could do, I know there are different depending on the bases. Maybe you could put like the exponential with a base of 2 and the logarithm with a base of 2, just so you can see how those look. But if you put those on your sheets, then that'll help you. It'll be a good reference for you for the future. Okay, because we're going to add some more to this later. Sine, cosine, and tangent. Alright, so just to wrap things up here, remember we always hit the point 1, 0. We're always going to hit the point, whatever A is, and 1. Okay? The domain is always x is greater than 0. The range is the real numbers. Already said the x-intercept. Okay? The x-intercept is 1, 0. There is no y-intercept because we have a vertical asymptote. Okay? It's continuous, which means there aren't any, once we're in the domain, there are no poles or asymptotes. And then it's constantly increasing. It's starting, so the further you go to the right, it's going to keep going up. Okay? And then remember, this right here, it's the reflection of the graph of the exponential function, or the exponential function had a horizontal asymptote on the x-axis. It went through the point 0, 1, okay? But it's the reflection across this line, y equals x. That's what makes these, what? Inverse functions of each other, okay? All right, so what I want to use the last little bit of time we've got here for, which is, we've got about 4 more minutes. I want to let you guys get started looking at these, okay? Here we're translating these into logarithmic equations, so it's the opposite of what you did on last night's homework for these first few. Here you're recognizing the transformations to match the graph with its equation. And then you've got some other transformations. And then here, I've got screenshots here, but use your calculators. For these ones, you can use your calculators for all of these. And when they say approximate any relative max or mins, like here, there's going to be a min point because it's going up. All right. Use the actual calculator and the actual like calculate max or calculate min function to find the exact. You don't need to just approximate, but get used to using your calculator functions and you're comfortable finding those max and min points or zeros and whatever. Okay? So, we'll let you guys get started with those for the last couple minutes here. All right. If you got questions, we can answer those.